Welcome to the fifth session of this polynomial series. In this video, we introduce the concept of multiple zero, complex zeros, and the complex conjugate theorem. We will apply these theorems together with the relations between polynomial zeros and its coefficients through 4 worked examples. Hello, math champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything. Welcome back to the series of polynomial. This is the fifth session of this topic. In this session, we are going to continue focus on solving equations using the relations between roots of a polynomial equation and its coefficients. In the meantime, we also encounter the skills of handling the complex roots and their modulus. The first example is a cubic polynomial function px, which equals ax cubed plus bx plus c. The question here is to find its coefficients a, b, and c, given that it has a multiple 0 at the value of x equals 1, and it has a remainder of 4 when divided by x plus 1. According to the remainder theorem, the values of 1 and negative 1 are substituted into the variable of the polynomial px. In this way, two simultaneous equations are established, and we find c equals 2, a plus b equals negative 2. Since the cubic polynomial px has a multiple 0 at 1, it can be expressed as a multiplies x minus 1, or in parentheses squared multiplies x minus m, or in parentheses. Here we assume m is the other 0. After being expanded and rearranged, the coefficient equating method is applied to establish simultaneous equations again. So we have the relations such as a times m plus 2, or in parentheses equals 0, a times 2m plus 1, or in parentheses equals b, negative am equals c, and the a plus b equals negative 2. After solving the simultaneous equations, we find the values of m, a, b, and c as shown on the screen. We continue on example 1 here, but with an alternative approach. Based on the polynomial function px, we write down its derivative function p prime x. Since px has a double 0 at x equals 1, both p1 and p prime 1 are equal to 0. Due to px has a remainder of 4 when divided by x plus 1, we have the equation of p minus 1 equals 4. According to all above, we have 3 simultaneous equations established. A plus b plus c equals 0, 3a plus b equals 0, and negative a minus b plus c equals 4. The simultaneous equations can be easily solved by adding equation 1 to equation 3, so both a and b are cancelled out in this way, and then we have c equals 2. After back substituting c into the equation 1 or equation 3, we can calculate the values of a, b, and c as shown on the screen. Example 2 shows a quadratic polynomial with two complex zeros. One is a plus bi, and the other is a plus 2bi, where both a and b are real numbers and b is greater than 0. There are two questions follow. The first one asks us to find the values of a and b. The second question is to express px as the product of two quadratic factors with real coefficients. Since the coefficients of the quadratic polynomial are all real numbers, If a complex number is a zero of the quadratic polynomial, its conjugate complex number is also a zero of the quadratic polynomial. So we know both complex numbers a minus bi and a minus 2bi are also zeros of the quadratic polynomial px. According to the relations of quadratic polynomial zeros and its coefficients, the sum of all zeros equals 12. So we find that a equals 3. Since the product of all the zeros is equal to the constant term of the polynomial, which is 130, we back substitute the value of a into the equation and then calculate the values of b that are 1 and -1. Since b is greater than 0, so b equals 1. After calculating the values of both a and b, the quadratic polynomial px can be expressed in its factored form as shown on the screen. After being expanded, we find the two quadratic factors of the polynomial px, which equals x squared minus 6x plus 10, or in parentheses multiplies x squared minus 6x plus 13, or in parentheses. Example 3 shows the polynomial function px equals x to the power of n plus 1 minus n plus 1, or in parentheses times x, then plus n, where n is a positive integer. There are 3 questions in this example. The first one is to show that the polynomial px has a double zero at the value of x equals 1. The second question is to show that the polynomial px is greater than or equal to 1 when the variable x is greater than or equal to 1. The last question is to factorize the polynomial px when n is 3. As for the first question, since px is equal to x to the power of the sum of n and 1 minus n plus 1, or in parentheses times x plus n, after replacing the polynomial variable x by the number 1, we find the polynomial px equals 0 at x equals 1. In addition, we differentiate the polynomial px, which result in n plus 1, or in parentheses multiplies x to the power of n minus the sum of n and 1. After substituting 1 into the variable of function p prime x, we find p prime 1 equals 0. Hence we have proved the polynomial px has a double zero at x equals 1. As for the second question, since we have the derivative function p prime x, we know that when x is between 0 and 1, p prime x is less than 0. When x is greater than 1, p prime x is greater than 0. When x equals 1, p prime x equals 0. So it proves that the polynomial function px is greater than or equal to 0 when x is greater than or equal to 0. Px equals 0 when x equals 1. Here we continue on question 2 of example 3. An alternative approach for question 2 can be done through the expression of p double prime x, which equals n times n plus 1 times x to the power of n minus 1. Obviously, it is greater than or equal to 0 when x is greater than or equal to 0. Therefore, the polynomial px is a concave function and its minimum value is 0 at the point of x equals 1. Hence, the polynomial px is greater than or equal to 0 when x is greater than or equal to 0. As for question 3, since n is 3, the polynomial function becomes x to the power of 4 minus 4x plus 3. As we know that the polynomial px has a double zero at x equals 1, px can be expressed as x minus 1, or in parentheses squared, multiplies another quadratic factor qx. Hence qx can be obtained by a long division of px divided by x minus 1, or in parentheses squared, which is x squared plus 2x plus 3. Alternatively, we may factorize the quadratic polynomial directly by subtracting 1 and adding 1 at the same time, as shown in red on the screen. Here we proceed with the basic factorizing technique and obtain the factorized expression of the quadratic polynomial px as shown on the screen. Example 4 shows a cubic polynomial px. Both of its leading coefficient and constant are 1, and both of its quadratic and linear coefficients are q. Here q is a real number. The polynomial px has 1, 0 at x equals -1. There are two questions in this example. The first one is to show that if alpha is a 0 of the polynomial px, then its reciprocal is also a 0 of px. The second question has two sub-questions given the criterion that alpha is not a real 0 of px. The first sub-question is to show that the modulus of alpha is 1, and the second one is to show that the real component of alpha equals the result of 1 minus q divided by 2. Since alpha is a 0 of px, the polynomial equation becomes alpha cubed plus q alpha squared plus q alpha plus 1 equals 0. Now we replace the alpha by its reciprocal, so we have the expression of the reciprocal of alpha cubed plus q over alpha squared plus q over alpha plus 1. After combining these terms by making them the same denominator, we find the numerator is just p alpha, which equals 0. So the reciprocal alpha is also a 0 of the polynomial px. Here we continue on question 2 of example 4. According to the conjugate root theorem, the conjugate of alpha is also a 0 of polynomial px. So the conjugate of alpha equals the reciprocal of alpha, which results in alpha times its conjugate equals 1. Hence, the modulus of alpha equals 1. As for the second sub-question, we factorize the polynomial px and obtain the factorized form of the polynomial as x plus 1, or in parentheses multiplies open square bracket x squared plus q minus 1, or in parentheses times x plus 1 close square bracket. Since alpha and its reciprocal are conjugate roots of the quadratic, x squared plus q minus 1 in parentheses times x plus 1. So we apply the quadratic formula to find the expression of the roots of alpha sub 1 and sub 2. It can be seen from the root expression that the real component of either alpha sub 1 or sub 2 is equal to the result of 1 minus q over 2. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.